We're going to discuss on the topic application of integrals. This topic deals with finding the area under a curve bounded by the x-axis and the abscissas x is equal to a and x is equal to b. Let's see how it can be graphically represented. Consider the xy plane. Now in this xy plane, the curve y equal to f of x is shown as such. Now this curve is bounded by the abscissas x is equal to a and x is equal to b with the x-axis. Now the shaded region that you see on the graph is the required area that you are supposed to find out. The area is given by the expression integral a to b y dx. Integral a to b y dx. This expression you have seen in chapter 7, definite integrals, and this expression is also called the area function. Now let's discuss a small example with regard to the area function integral a to b y dx. Example 1, we are considering the equation 2x minus y plus 8 is equal to 0. You have studied straight lines in grade 11. There, the equation of a line is ax plus by plus c is equal to 0, right? So, this equation represents a straight line. As you can see on the xy plane, this is the straight line that is represented by the equation 2x minus y plus 8 is equal to 0. Now, we're going to find the area bounded by the straight line with the x-axis and the first abscissa x is equal to 1 and the second abscissa x is equal to 3. Okay, now I'm going to show you how to find the area. This area is found out by the expression area is equal to integral 1 to 3 y dx. From the equation that is given to you in the question, the expression for y is y is equal to 2x plus 8. The expression is y is equal to 2x plus 8. Substitute y is equal to 2x plus 8 in the integral. You will have integral 1 to 3 2x plus 8 dx. Now we have to find the integral of 2x plus 8, which is equal to x squared plus 8x with 1 to 3. X squared plus 8x with limits 1 to 3, and you know from chapter 7, grade 12, how to substitute the limits in the integrated form. It is going to be 9 plus 24 minus 1 plus 8. The final answer is 24. So the area bounded by the line with the x-axis and the two abscissas is 24. That is the most simple example you could do with the area function integral a to b y dx. The next concept is based on the understanding that the curve need not always stay above the x-axis. Sometimes the curve can be below the x-axis. In such a situation, if you apply the area function as such, that is integral a to b y dx, the answer of the integral is going to be negative. So when the curve is below the x-axis, graphical situation is when you have an xy plane, okay, such as xy plane is over here, and you can see the curve is below the x-axis now. When the curve is below the x-axis, the area from the curve to the x-axis between the abscissas x is equal to a and x is equal to b. We know the value of the area should always be positive. But if you try to compute the area in this situation, the area value is going to be negative. So when you can see that graphically the bounded area is below the x-axis, you apply a modulus in the formula. So in this situation, the expression for area is given by area is equal to modulus integral a to b y dx. This expression will give you the answer for area in positive terms. So keep in mind, whenever you are bounded area is below the x-axis, you're supposed to apply modulus in the expression for area function. Okay, now let's go for an example. Let's take example 2 here. The expression is y is equal to minus x squared minus 3. So this is a quadratic equation. The coefficient of x squared is negative. So definitely this parabola is going to stay below the x-axis and the values are going to be shown as in the parabola over here. Okay, now if I'm trying to find the area between the abscisses x is equal to 2 and x is equal to 4, then the area would be over here. Yes, I'm going to find the area below the x-axis. So definitely if I apply the area function, it is going to be negative. So my formula is going to look like area is equal to modulus integral 2 to 4 minus x squared minus 3 dx. This is the expression for the application of integrals area function. Integral 2 to 4 modulus minus x squared minus 3 dx. And what is the integral of this? Minus x cube divided by 3 minus 3x from 2 to 4, but definitely keep the modulus. Okay, apply the limits. It's going to be minus 64 divided by 3 minus 12 minus 8 by 3 minus 6 and the modulus. The answer is going to be negative 74 divided by 3. So you keep it as positive 74 by 3. Okay, so this is the situation where the area lies below the x-axis and the integration of that result will be always negative. So you have to keep it in modulus and the answer would be positive. Now let's consider the next instance where your graph of the function is not going to give you the area bounded with the x-axis. It is not always compulsory that the area to be bounded with the x-axis. Area might be sometimes also bounded with respect to the y-axis. Then in that case, you will not be considering the abscissas, you will be considering the ordinates. Okay, now look at the situation over here. This is the xy plane that you can see over here, and the graph is going to be x is equal to g of y. Okay, the graph is going to be x is equal to g of y bounded with the y-axis and the ordinates y is equal to a to y is equal to b. In such a situation, the graph will be giving you area which can be obtained by the expression area is equal to integral a to b x dy. Okay, so in this instance, you will be integrating a function in terms of y. So you will rearrange the expression given to you in the question as x is equal to g of y. Another function in terms of y. Understood? This is how you consider the situation when you're trying to find out the area bounded with the y-axis and with two ordinates y is equal to a and y is equal to b. Now let's consider a situation where the area divided by the x-axis and the two abscisses are one above the x-axis and one is below the x-axis. So the curve is fluctuating below the x-axis and above the x-axis. So when you're trying to find a situation where your area is bounded between two values of abscissa and the x-axis, where one portion of the area is below the x-axis and one portion of the area is above the x-axis, the normal intuition tells you is you always tend to find the areas of both the region and you simply add them. You say that's the algebraic sum of these two areas. Okay, but sometimes there is a problem over here. When the area is below the x-axis, when you take the algebraic sum, you will not get the actual area. Okay, because the area below the x-axis, as you have seen before, is going to be negative. So the algebraic sum does not actually represent the area bounded by these curves. So in such a situation, you have to find the area of each region separately and add them, and don't forget, you add the modulus of the area below the x-axis with the area above the x-axis. So when you find the area below the x-axis, you will find the area with the modulus. Okay, consider the graphic situation over here. I'm drawing the xy plane. Yes, you can see the xy plane. Now see the graph over here. See, it's going below the x-axis and then climbing up above the x-axis. Now consider the abscissa over here. X is equal to A and x is equal to B. You can see area A1 and area A2. Now area A1, very clear, is below the x-axis. So when you find the area A1, you are supposed to take the modulus. And when you're finding area A2, you keep it as such because it is always going to be positive. So the expression for area is going to be what? As usual, you will find A1 and A2. So the total area is modulus of A1 plus modulus of A2. This is how you find the area of such a graph. Now let us see a situation where the area bounded by the graph is both below the x-axis and above the x-axis. Example 3. The equation is y is equal to x cubed minus 6x squared plus 8x. When you talk about the solutions for this equation, that is when you equate it to 0, the values of x are 0, 2 and 4. And so this graph is going to cross the x-axis at the points 0, 2 and 4. So this is going to be 0, this is going to be 2 and this is going to be 4. Okay. Now I'm trying to find the area bounded by this graph between the abscisses x is equal to 1 and x is equal to 3. So this area we are talking about is these two. So this is my A1 and this is my A2. Now you can see that A2 is below the x-axis. So when you're finding the area of A2, you have to apply modulus. So let's see what is the area of A1. A1 is equal to integral 1 to 2 x cubed minus 6x squared plus 8x. The expression for the integral is x power 4 divided by 4 minus 2x cube plus 4x squared from the limits 1 to 2. Okay, from the limits 1 to 2. And the value of this integral is 23 divided by 4. The value of this integral is 23 divided by 4. Okay, now let's go for A2. Now A2 is definitely below the x-axis. So if it's below the x-axis, it is going to be negative. So when I'm applying for A2, I'm going to be applying a modulus function for integral from 2 to 3 x cube minus 6x squared plus 8x. Okay, and this expression is already integrated before. It's going to be x power 4 divided by 4 minus 2x cube plus 4x squared with the limits 2 to 3 and you have a modulus. And the value of this integral, when you compute, it is going to be modulus of minus 7 by 4, that is equal to 7 by 4. Okay, now I got A1, I got A2. If you did not apply modulus for A2, you will be subtracting A1 and A2, not adding. But since you applied modulus, your area is going to be total area is going to be what? Total area is equal to A1 plus A2. Okay, what is A1 plus A2? You're going to add the two values, 23 divided by 4 with 7 by 4. 23 divided by 4 with 7 by 4. The answer is 15 divided by 2. 15 divided by 4. That is a total area bounded by the x-axis and the curve with the abscissas x is equal to 1 and x is equal to 3, where the area lies above the x-axis and below the x-axis. Now let's consider a situation where you're trying to find the area between two curves. Not always the question will deal with one curve. Okay, you're going to talk about area between two curves involved in the same question. Consider a situation where y1 is f of x and y2 is g of x. I'm talking about a situation where the function f of x is greater than the function g of x. So when you plot it on the xy plane, f of x is going to stay above the x-axis. See, consider graph here, the xy plane. Now in this xy plane, y1 is equal to f of x and y2 is equal to g of x. So here f of x is above g of x because f of x is greater than g of x. Now we are trying to find the area bounded between these two curves and the abscissas x is equal to a and x is equal to b. So this shaded region is the region we are talking about. Now we know that the area function gives the area from the curve to the x-axis. So if I integrate a to b for y1, I will get the area from f of x to the x-axis. Now if I talk about the area with respect to y2, it is going to be from the curve g of x to the x-axis, right? So if I want the area between the two curves, it is going to be what? Area is equal to integral a to b y1 minus y2. y1 minus y2. So the total area from f of x to the x-axis minus the area from g of x to the x-axis. This is how you find the area between two curves. Now let's see a different example. A situation where you already know how to find the area of the area under the curve or area included by the curve. Now, the example depends on how to find the area using application of integrals area function. See, let's see example 4 now. Example 4 talks of the area of a circle. Area of a circle, you know from geometry, in smaller classes, you have learned that area of a circle is equal to pi r squared. So if I know the radius of the circle, I can find the area of the circle. Now this is x squared plus y squared is equal to 4. From grade 11 conic sections, you know that this is the standard equation of a circle with center, yes, center 0, 0. Yes, so this is the center 0, 0. Okay, and the radius r squared is equal to 4, so r is equal to 2. So this is a circle with radius 2. So if this is a circle with radius 2, what are the coordinates over here? Coordinates over here is 2, 0 and the coordinates over here is 0, 2, no doubt. So because this is a circle with radius 2. Now I want to find the area of this circle. So according to pi r squared, the answer is 4 pi. The answer is 4 pi. How can I do this with integrals? Now you can see that the circle is with center 0, 0 and the quadrants or the axis divides the circle into 4 equal parts. Okay, so can I say this is area 1, area 2, area 3 and area 4. If I find the area of one of the portions and I multiply it with 4, won't I get the area of the circle? Okay, now the expression is x squared plus y squared equal to 4. So y is equal to square root of 4 minus x squared. Y is equal to square root of 4 minus x squared. So this is the curve. This is the curve. Y is equal to square root of 4 minus x squared and the abscissas are x is equal to 0 to x is equal to 2, right? The abscissa 1 is x is equal to 0 and the abscissa 2 is x is equal to 2. So my integral area is going to be, area is equal to 4 times the integral from 0 to 2 square root of 4 minus x squared. Revise the concept of special integrals that you learned in chapter 7. The formula of square root of a squared minus x squared. The formula of a squared minus x squared is x by 2. A squared minus x squared plus a squared by 2 sine inverse x by a. I'm going to apply this formula. If I apply this formula, it's going to be x by 2 root of 4 minus x squared plus a squared by 2 sine inverse x by 2. Okay? The integral limits is from 0 to 2. Now, if I apply the limits over here, the first expression is going to be 0. Okay? We have a 4 over here. Don't forget about the 4. We have to multiply it with 4. We have to multiply it with 4. When you multiply it with 4, the answer, when you apply 2 here, 4 minus 2 squared is 0. When you apply 2 here, I will have 0 plus 2 sine inverse 1 and minus, when you apply 0, this expression is 0, sine inverse 0 is also 0. So the entire lower limit is 0. That is going to be 2 into sine inverse 1. That is 4 into 2 sine inverse 1 is pi by 2. So the answer is 4 pi. Can you see I got the same area over here? So application of integrals is going to help you to find the area of any such curves. Area of any such curves, especially when it's a combination of curves, that also is possible to find. Thank you.